Hi, my name's Adam, and in this video we're going to look at the Fin language, some of the features and syntax. So let's get rolling. Now this is actually part 2 of a 6-part video series. If you're not super keen on just the syntax of the Fin language, you might be better served to skip into the next video, which is really cool. Multiple controller simulations for the win. I actually really like that one. But that said, there's some cool stuff in here too. Safety features, and actually, yeah, let's just talk about some of the features at a quick high level before we dive into them. No more header files. I know C++ is working on that right now. Make our lives easier, just write your code once. But again, the compilers as an embedded system developer that I have access to aren't going to see those benefits for quite a long time. With Fin, we get that now. We're going to talk about some null stuff, non-null types, preventing pass-by-copy mistakes, null analysis. We're going to talk about some function stuff, out parameters, tuples, named arguments, simple generics. Then there's some safety stuff, safer strings, arrays, memory access, error handling, overflows, non-blocking assurances, data thread safety, and then also how to defeat that safety stuff that comes by default when you really don't need it and you just want that extra efficiency and performance. And then supporting code generation and portable serialization and deserialization. All right, write it once. No more writing function prototypes, definitions, and creating header files. Just write your code once and move on. It's the goal, right? Live a happy life. So here's a simple little example of some Fin code. We write some documentation here. There's our everything. We don't need to spend a lot of time on this, but it's really nice. And there's no worry or question about keeping .h and .c documentation in sync. And the endless, stupid, pointless arguments over, like, should it be in the H file? Well, is it a library or is it internal? Should it be in the C file, like by the implementation? Again, sometimes people put it in both, but then one gets out of sync and it's just a pain in the butt. We don't have to worry about that with Fin. No null checks needed. So a Fin object reference is essentially a C pointer that can't be null. And it's very similar to C++ references. So if we look in here, we get a packet object. It's basically a non-null pointer, and we don't have to worry about any null checks before we use it or pass it on. Now, C's pointer ambiguity, because we use pointers for many different things like optionals and input or output parameters. It's often a common source of errors and sometimes results in unnecessary error checking. So here's a tiny little example. Well, let's pop this out here too. So every time you write a C function that takes a pointer, you need to decide, is a comment explaining nullability needed? Some comments also rot after you write them. And is a null check required? What do we do if there is an unexpected null that it gets passed in? So with Fin, it's impossible to do something like that. Like, you can't pass a null to this function. It just won't compile. But with C, we have to use comments and like doxygen or something like that to specify that this must not be null. Now, library writers might still have to protect against it, or may want to. If it's your internal code, maybe you choose not to. But yeah, it's just like all this extra headache and team discussions, or like working with junior developers who aren't aware of your conventions, or if you're using different libraries that have different conventions. It's just a pain in the butt. Really, I just want to pass this darn packet that can't be null. I don't need to worry about any of that garbage. And speaking of passing things by reference, there's a common problem that happens in C, which is you might pass a struct by copy. And in C++, this is a very common mistake. And sometimes you mean to pass a copy of an object, but sometimes you really don't. And with C, with C++, it's more difficult to spot, or it can be at least, because we've got references. So in the using code, there's a method or a function invocation that takes a packet. I have no idea how packet is passed. Is it passed by copy? Is it passed by reference? The only way to find out is to go check the actual the function definition or implementation. Now, also here, did somebody just forget to type the ampersand to receive this by reference? This does happen quite a bit. You see it on coding blogs too, or video YouTuber bloggers were like, oh, I accidentally forgot this one thing and it messed me up for like 5 hours. Yeah, it does happen. But this is also annoying because this is the most kind of like default syntax. So like by default, you're just writing packet, your type, and then your the actual variable name. Do we really want to be passing structs by copy as our default? I don't really think so. That's not, it's pretty inefficient if you've got structures that are of like a decent size. So fin passes objects by reference, not by copy. Primitives like ints and floats and doubles, those are still passed by copy. And in fin, we take the opposite approach of what C and C++ do. If you want to pass a copy or receive something by copy, you have to make it explicit. So there's no accidental copying happening. So in your function declaration or definition, it's very clear, hey, I want some memory for a packet. Give me a copy of this. But also the using code, it requires an explicit copy. So there's two different variations of this. We'll start with the first one here, which is you have to say mem.copy on the packet as you're passing it to the function. Maybe in the future, we could have some syntax that looks like this. All right, null analysis. So in fin, you can pass parameters that can be null. You just have to check before you use them. So in this example here, we've got a packet that can be null. So we just add that little question mark there. That's how you basically specify that. It can be null, but it might not be null. But we try to use it. We try to send it to the UART or give it to the UART to send. And the UART doesn't want a null packet. And so the fin or C# compiler will throw an error there and say, yo, you can't do this. You got to check to make sure it's not null. Now there's two ways you can handle that. One is the compiler is smart enough to detect you're just doing a basic null check. And it's smart enough for a lot of different patterns too. So you could do an early return instead, or just do it simply like this. And in some cases, maybe your code has kind of gotten away from you a little bit. It happens. And you actually know at this case that you want to receive a nullable packet, but you really know that it's not. You can just use the damn it operator here and say, damn it, I know it's not null, and the compiler will let you move on. Out parameters. So I would say that the out keyword is better than using comments in C or C++. And the next slide talks about tuples, which are helpful too for basically multiple returns. So in this example, little bit of code, really all we're doing is some division where we get out the quotient and the remainder. So the quotient is just like number, integer division, and then the remainder is, modulus kind of like division. So in C# or in fin, you have to specify that this is an out parameter, and at the call site too, it's quite cool. So you actually have to specify at the call site, hey, we're passing quotient to it, basically with a pointer underneath, but you see really easily this is an out parameter. And so the other thing to note here too is that you don't have to define everything beforehand. Like here we define quotient and then we pass it as an out parameter, but we can do that all in one here as well if you want to. If you hate this, that's fine. Sometimes it's really nice. So you can do it all in one. And then the equivalent part of this function, this is how it would look like in C, or how it could look. Now we have to rely on comments or maybe variable naming for people to pick up on to say like, hey, quotient is an out parameter, can't be null. Remainder, out parameter can't be null. Sometimes I see people write their comments over here. Sometimes it's named over here. But yeah, again, it gets difficult when, in this case, it's not so bad because you see, okay, input, output. but sometimes you're actually passing a structure like a packet and expecting an output as well. So some of your pointers are inputs, some of them are output, and that's why in C you have to rely more on like your comments to help explain what's what. We don't have to worry about that in Fin and C#. The other thing that we have is we have support with for tuples, which allow an easy way of returning multiple things at once. And they're really just a convenience. You could also create your own class to do the same thing. So this syntax here is, it's a public function that returns a tuple, which is like basically a convenient way of declaring a structure that has a quotient field and a remainder field. And then the rest of this is the same. There's the syntax for returning. This is the first field quotient, and this is the second field remainder. If you want to, you can actually specify the field names here too, to make it extra explicit and a little bit more future-proof. And this is how you would use that code. So you could say result equals divide, and then result here is that tuple. So you can get access to the quotient like this, or the remainder like this, but you can also destructure those variables from the tuple. So in this one statement, we basically declare quotient as a variable and remainder as a variable, and they're their own variables here. Yeah, it's pretty cool. It's something that could be useful for doing kind of like a Go-like or a Rust-like error handling if you wanted to, in a relatively efficient way, so you don't have to define a whole bunch of structures. Named arguments. I think these are actually really helpful, especially if you've got a function that takes multiple arguments of the same type. So maybe this is in some sort of like geometry or visualization library where we're taking objects x, y, width, and height, and they're all doubles. And so you can't rely on different types to make sure that you get the order correct. And if we look at the usage of it here, this is Fin or C#, even though it's declared as x, y, width, height, by specifying the name, we can go x and then width, y and then height. And this is actually really helpful if you're working with different libraries that use these kind of two different regular conventions. So sometimes libraries will go x, y, width, height. Sometimes they're more often to go x and then width because they're, x related, and then y and then height. So yeah, it aids in readability and can help prevent bugs. I've definitely seen bugs happen because people got the order wrong, and yeah. Simple generics. This is huge, something that I really miss in C. If you write a queue class or another container like a linked list or whatever, you got to do it for every single different data type. So most people I know, maybe they implement an int queue first, and they go along and they use that until they need a byte queue, like a uint8 queue. And so they copy paste their int q.cn.h and rename them into byte q.cn.h. And that works fine. You find all, replace all, until you find a bug or want to make a change in one. So maybe you're working mostly in byte queue at the time, so you update it, fix it, but then you forget about int queue. And this gets worse the more different data types that your containers support. It just, it sucks. So I've done a decent amount of preprocessor abuse in my own personal projects. I don't do that at work, just like experimenting with it. And it's interesting, it's really cool, but it's also really clunky, it's awkward, and for people that aren't familiar with it, they hate it. And I understand why. Like, there's a lot of hate towards kind of abusing the preprocessor in C. Some people love it, some people hate it. I don't think it's a really good approach to take if you can help it. So with C++, actually, you know what? Hold on, let me just follow the slides here a bit. There are other, I would say, suboptimal solutions. You could allocate everything with a heap and use void pointers in all of your containers, or you could use unions. Anyway, we don't have to worry about any of that with Fin. It just works. Yeah, it's a generic. Here's our queue that can take a type. It could be an int, could be a structure. Nice and simple. Now, I'll note C++ does have this ability for sure. The syntax is a little bit funky if you're not used to it for C++. And the fin/C# generics are definitely not as powerful as C++ templates, but they're also way nicer to use. Now, I'm not a C++ expert at all. I've spent a lot of time with C and other languages. I've written like tens of thousands of lines in C++, not in the hundreds of thousands or millions. So like, I'm not a guru. This is my experience. But in my experience, C++ templates tend to lead to horrific compile time errors. So if you've got, especially as you write more and more code that goes deeper and deeper into templates, or like a queue that maybe you might have like a different data structure that uses another data structure to implement some more interesting ones like a hash map or something like that, or a hash map that takes a list. Anyways, as we start to do that more and more in C++, your code turns into like duck typing because the C++ compiler doesn't actually check your template code until you instantiate it. And this breaks refactoring, and it tends to just get difficult. And even people that I know who write C++ professionally, they really complain about C++ templates causing just horrific compile time errors. And I remember, just a short little story here. I remember when I was in university, and Bob McLeod had this cute little comic on his door where he said, like, here's my algorithm for writing C++. Write a single line, compile, fix the errors, and then repeat. And I always thought that was kind of ridiculous until I started going down the deep C++ template path where, yeah, I do get it. The quicker you find your mistake, the less horrific your compile time errors are with C++ and templates or metaprogramming. I don't want it to sound like I'm dunking on C++. I think it's a really awesome language, and I do use it for some of my other code generation techniques. It's just that it has issues too, and Fin can help us get around those. So with safer strings, yeah, basically everybody knows that C strings are a very common source of bugs. And so Fin is going to support regular C-style null terminated strings because we want that like optimal interop with C. But we will also add safer strings that keep track of length and prevent issues. Now that said, the Fin string lib is going to focus initially on non-heap string functionality. So you can create a string on the stack, it doesn't touch the heap, and it still gives you all the benefits that you want. Safer arrays. C memory safety, always a concern. Just like with strings, we're going to support C-style naked arrays, but we will add safer arrays that track their own length. There's some open questions there. One of them is, if we have a Fin array, it basically is going to bundle together a length, like how big the memory actually is, so we can do some safety there. But what size is that primitive that's tracking the array length? I'm not sure the best way of handling this. So maybe we have different types for like array, I don't know, like an array U8 or something. I don't have the best naming of it, but like sometimes I've got a teeny tiny little array, and so I just want to use the smallest possible primitive to keep track of that length. I don't want a full int32. Yeah, so open to suggestions on naming and how we could support that. Maybe we just do it at compile time so that your Fin code doesn't worry about it, but it just gets generated with the optimal size for it. And also it's an open question of how we want to handle out of bounds access. Do we want to panic and just crash? I don't really want to, but I don't know. That might be an option, or call an error handler, I guess. Do we want to ignore it in certain builds? So maybe it's only enabled for debug, but not release. Do we want to throw a lightweight exception? Trigger alert. We are going to talk about exceptions in a little bit, but don't throw your popcorn at me yet, or whatever is close to you, maybe a banjo. Yeah, lightweight exceptions. They're not like C++ exceptions, and they will be optional, not like a required thing. All right, let's keep on going. But longer term, I want to one day support fixed size arrays like the C++ standard array, where it combines like a data type and the actual size. So there's potential syntax ideas of how we could get C# or fin to support this. We could have array5 of type int, basically mean, yeah, this is an array of 5 ints. And with C# code source generators, we could do this. It can detect that, hey, you wrote array and then a number. On the simulation side, it'll generate all the C# code that you need to make that happen so that your simulations still work. And then it's really easy on the fin transpiler side to support this. Another thing we could explore, and I'm just throwing this out here to maybe get different ideas going, is something closer to what the C++ standard array does. You've got an int. We can't put a 5 here because that's not valid C#, but you could go like L for like literal 5. Anyway, it's definitely not as nice as C's syntax for declaring an array of a certain size, but then C also messed it up too. If you look up the Walter Bright article on, or just Google it, C's biggest mistake, trying to pass a fixed size array to a function sucks because it decays into a pointer. And then people try to do size of on what looks like it's a fixed size array, but it doesn't work. And so some compilers like GCC will actually detect that because it's such a common issue that people run into. But other compilers, lots don't actually catch that. Anyway, so yes, it's not the perfect syntax here, but I think we can come up with a compromise that fixes a lot of the issues that we have in C as well. All right. Also a future thing, arithmetic overflow. It's a common source of annoyance for programmers and code reviews, primarily with control systems. So in my day job, we build controllers and write C programs for heavy machinery, basically. And if we've got a control loop, we want to be careful. We take in some sensor logic, we apply some filtering or like different algorithms to it, and then we basically actuate different hydraulic outputs. Now, if there is if there's an overflow in some of our calculations or filtering, that's a big deal to us, like going from positive down to negative or positive down to small. So that is a real concern for us, and it slows us down as programmers and also in code reviews. So we've got some options here. Oh, not to mention, especially if you're doing some sort of math before you do an allocation, like from the heap or something else, you definitely got to be careful with your calculations before you deal with memory as well. So we could potentially add special types that throw on error on overflow, and this might be the default. This is probably what I'm leaning towards. If you look at other programming languages, Rust only has this in debug builds, not at runtime. A lot of people are upset with that because they have situations similar to mine where like I really do care about it at runtime. And if you look at some of the brilliant people who wrote C# or were involved in the early C# days, in C# you can put in like a checked or unchecked block to determine whether overflows are caught. But looking back, some of their opinions are that they probably should have made an overflow an error by default and allowed people to escape. So that's kind of the way I'm personally interested in. I'm not as keen on like just crazy fast performance. I want good performance. I want solid performance. I want to be able to disable those checks when I don't want them and I don't need them. But really, I want that safety too, because it's important for at least my work. And then maybe we also add special types, like, I don't know, maybe it could be, just throwing out an example, I haven't really thought this through, like fast U8 or something like that doesn't care if it overflows. It's just like regular. It's meant to do overflow and kind of that modular behavior. And then we could also add special types that saturate. So it's not an error. They just get to their limit and they stay there. In the future, I'd really like to add, after we get the important stuff done, I'd like to add static analysis and hints so that we can ensure that there is no overflow at compile time. so that we can omit all the costs for checking. Like ideally at runtime, there are no compile time, or sorry, blah, 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 blah. I'm talking too fast. I really, really like this feature, but I just need to slow my brain and my mouth down a tiny bit. Ideally, the fin compiler, based off a little bit of hinting from the user, will be able to determine that there are no possible overflows, so we don't have to add them to runtime. That I think is the ideal situation. And there are some interesting approaches that we could look at. So this one's not compile time. I believe this is just a runtime. This one is at compile time, and I actually heard about this from listening to the CPP Cast podcast, which is excellent, by the way, big fan. But there's some interesting criticisms of this library. Like the dude is smart for sure. David Stone, he's put a ton of work into this, but like very few people have used it. And some of the criticisms are mostly around compile time. Oh, good, my compile times aren't long enough already. Let's make every single integer a template. So I don't think it's that the idea is bad. I think it's that we have to be careful with the implementation. And so maybe we can have the checks not be run when you're in your regular just like iteration or like write code test, write code simulate, write code test, that kind of thing. Maybe it doesn't happen all the time. Maybe it's something that you do before you transpile to C or something else. We want to, as much as possible, keep the development cycle fast. And that's actually one of the other issues with Rust too, is that it is typically a very slow compile time. So I want to, as much as possible, try to get the best of all the worlds. Have that fast development cycle, but also have that safety. But don't pay for all like the intensive compile time checking and all of the static analysis every single time you just want to make a small tweak. Non-blocking assurance. So if you write interrupts, or if you have people on your team that are also dealing with interrupts, the common knowledge is keep your interrupts short and sweet. But sometimes we do call functions, especially like on a can interrupt or something like that, or like if you're not familiar, like can bus message interrupt. Now, it would be really nice if Fin could check all code paths and ensure that none of them actually block, because we really don't want to block inside an interrupt. So maybe that could look something like this, where we've got annotation at the top saying non-blocking. This is some sort of interrupt here. And then Fin could go through and make sure that, hey, no possible way for any of these functions or the functions that these functions call that call other functions to block. That would be nice. So that would be helpful. And it might seem like I'm being kind of ridiculous here, but I've definitely seen cases in my own experiences where it's some of the code is started by person A, then person B takes over, then person C takes over, and then person D takes over. And so like if you look at any one developer, maybe the last developer there, they don't have necessarily a full super deep understanding of all of the code. And actually, yeah, let's just read it out here. So sometimes there's a rare error branch is taken inside of your interrupt, and the handler for that function wants to print a debug message. Now, the writer of that function that is printing the debug message didn't originally anticipate it being called by an interrupt. Maybe the interrupt code was written and it called that helpful function before that helpful function added a debug message, and then person Z comes along and it's their function that they're not aware of is being called by an interrupt, and they're debugging it or whatever, and they add a debug message. And so this has happened. I've seen this happen before, where 99% of the time that interrupt works great. 1% of the time there's some sort of error, a regular reasonable runtime error, and then it goes into this other branch which blocks, and then fun times ensue. So I would love this one little simple annotation that would just catch that right away and say, yo, hey, by the way, this one function calls that function that calls this function, which blocks. Please fix that. Not cool. Critical section audits, very similar to the interrupts we just talked about. Critical sections should be short and sweet, like an interrupt. But yeah, sometimes we do have to call some functions and do some processing in there. I think it'd be really helpful to have Fin be able to audit all code paths inside a critical section, including all of the call chains, and make sure that none of them can block or call like functions that could be an issue. So yeah, from FreeRTOS, which is what I primarily use, if you're inside a critical section, you must not call a FreeRTOS API function. And this is, yeah, it can just get away from you easily if you have multiple developers working at the same time. Yeah, especially if one person's maintaining that library, one person's working on kind of the lower level stuff, and then they rely on this library, and there's not perfect communication between the two groups. This can be an issue. Data thread safety. So I'm not sure how I want to implement this yet, but I do definitely want to be able to detect data concurrency issues, considering things like threads and interrupts. And in the easy cases where you've got a class that runs in its own thread, you can just add an annotation to it. Not that difficult. But it would be harder if you have a single class that is instantiated multiple times and has multiple threads. I'm not sure how I want to solve that yet, but I do know that I do eventually want to solve that. So in this harder case, one thing we could do, which isn't totally perfect, but gets us some level of protection, is that during simulation and testing, Fin can keep track of data and which threads it was accessed by. So if a block of data is accessed by multiple threads within that simulation, and Fin knows that it wasn't in a safe or critical section, it can throw an exception and say, hey, this code was hit by multiple threads. You should do some sort of, safety mechanism here. Now, safety escapes. So safety is going to be the default for us. We're not looking for pure blazing speed. We want correctness. And then in certain cases where we know that we don't need to be safe and the compiler isn't smart enough yet to be able to determine that safety isn't needed, we want to have a way to enable and disable like memory checks or out-of-bound checks or overflow, that kind of stuff. But it would be really nice to be able to do that without having to mark up the actual source code, because sometimes that source code is shared between multiple projects, and maybe project A knows that its call to library function B doesn't need to worry about overflow, but another project that uses that exact function does need to worry about overflow. So it'd be helpful to be able to do this maybe from like a config file or something. And it would also be really cool if we could, if Fin libraries as they're written can provide tagging or like some sort of tag so that the config can also disable checks in the library as well. We'll talk about this more later, but just an idea of where my mind is at right now. Okay, belay the pitchforks. I know lots of people hate exceptions, and for good reasons. I agree with all those reasons, but I still think there is value here that we should explore. We just need to do it in a different way. So yeah, there's a lot of dislike towards exceptions as they're currently implemented in some of the popular languages. The big one, hidden flow control. I totally get it, and I agree. It's hard to audit, and it also just sucks. If you're coming from like a safety perspective, and you don't know by looking at the code in a PR, or basically PR is the worst place because you don't have any IntelliSense to help you. Any single function anywhere or any method could pop off into an exception. I get it why people hate exceptions as they're done now. We have an idea on how we could get around that. Also, though, most embedded projects that I'm aware of that do use C++, they disable exceptions because the exception tables and unwinding data can be quite large. So my rough knowledge of this is that C++ wanted to have a zero cost for when exceptions aren't used with following the mantra of like, you don't pay for what you don't use. But when a C++ exception is thrown, there's a performance cost because you got to do all this unwinding stuff. And also just the data can get quite large. And if we look at another commonly hated feature, well, loved and hated, Java checked exceptions. They're interesting because unlike some other languages where you can just throw an exception and nobody knows what's happening anywhere, Java can force you through the compiler to make sure people know which exceptions can be thrown. Yeah, so cool idea. People have mostly kind of considered that to be a bit of a failed experiment though, and it often gets circumvented. But there is a way we can kind of get some of that benefit as well. Now in Fin, exceptions will be implemented in our generated C code more like an out parameter or maybe like a return code. It's not going to be heavy like C++. It's basically like how you would handwrite error handling in C, but you can use the syntax of exceptions. That said, I know people still are going to hate that. So the Fin library is aiming to support, like for string functions that might throw, we'll have two kind of branches. You could have like a try thing where it returns an error code, no exceptions, and then we can also have the exception path. And I'd like to support both of those. And leave it up to users. Again, my goal is not to force you to do things a certain way. It's to give you tools to use for the best job or for what you want to use. Okay, so lightweight exceptions. How do we address hidden flow control? Well, first of all, one thing that is really cool for us because we are generating to C. Holy crap, I've been talking a long time. Sorry, I should try to speed this up a bit. Because we're generating to human readable C99, when you look at the code that gets generated from your Fin code, the control flow is going to be totally easy to see there. You don't have to delve into assembly to see it. So that's one kind of bonus, even if we don't fix it at the Fin layer. At the Fin layer though, or level, we could require, and again, I'm open to thoughts and suggestions, prefixing your functions with MT for may throw. So that could look something like this. Maybe there's a get ID method, so we want to get an ID out of a packet, but if this packet is malformed or not the right length or something, it may throw. And we can also have pass that ID to another function, which is going to get a response, just a pretend example, from that ID, and it may throw as well. And then that response that we get, maybe we want to just immediately send it, and it may throw. Now, here's where I personally do like I see some of the benefits of exceptions. We can see that, hey, it's all visible here, but we also don't have to clutter our code with a whole bunch of if else for handling all of the error handling in here. Sometimes when I write code, I need to do that because I care about exactly every single error. But in this case here, I might not care at all where it fails. I just care that one step in this, block of like little algorithm failed, and that's good enough for me. So with an exception, that's nice. We can have like 10 or 12 or whatever different statements, and we can bundle that all into kind of one error handler. But what if we have a deeply nested function like D that adds new functionality that might throw? So in this case, let's say A calls B, which calls C, which calls D. Well, what do we got to do? Well, either you handle with a try catch that exception in D, or you prefix D and let the exception bubble up to the next layer. So if you did that all the way up the chain, you'd have to do all of these here. And because Fin has really solid refactoring, renaming these isn't that hard. It's a couple seconds work for each one. So not the end of the world, I'd say. Anyway, it's an idea. I think we got to try it or some variation of this and see how we like it. Support code gen. So even though Fin will make writing C code more enjoyable and faster, some projects still require a lot of boilerplate. Like some of the controllers that I work on, those projects for like a combine or something like that, sometimes we have like 300 different controller parameters, and that's just a lot of code. Like hand wiring all of that up, sometimes it feels like you're a data entry specialist. I'm not a programmer anymore. I'm just a monkey that like connects the dots between all these stupid parameters and all the stupid things that support the parameters and all the stupid things that use the parameters for data logging and all that kind of stuff. So I've written a bunch of code gen tools in C++ to help me, but I'd like that to happen in Fin. And then the other thing that people typically do without support for code gen in these cases is we just copy paste our way to victory, and a ton of mistakes too, to be honest. And really, engineers or programmers or tinkerers, really, we want to be thinking about the problem, blinking LEDs. We don't want to be doing cruft work that's like, not very helpful. AIs can help sometimes, but often I think the right answer is code gen. And in comparison with other languages too, like I think the approach that I want to take is to be more explicit with our code gen and have the generated code be a part of your project rather than something that's hidden from you as the user using powerful macros and templates and arcane incantations. Yeah, I'd rather write something simple that generates new Fin code that I can see, and also check into Bitbucket or Git so that people can review it as well. Yeah, so a goal of Fin, make it easier. Now, portable serialization and deserialization. We all know that we shouldn't rely on specific bit fields and struct layouts and padding, especially when we are doing like network or packet kind of stuff. We shouldn't use a memcopy on a packet, but lots of people do it anyways because the alternative is rather labor intensive and maybe the project just doesn't call for it. But the issue is it doesn't call for it at the time. So maybe your version of IAR and this STM32 works with the server. Everything is happy with how those packets are going back and forth. You go down that road for a couple of years, and then you add a new architecture, which doesn't have the same alignment or bit field, blah, blah, blah. And now you're kind of hosed. Really, I think we can make this easier. The Fin library can do something like, so some finlib, I don't know what it would be called yet, but you can just say deserialize to a packet from some bytes, and you can get a success there. Or if you want to enjoy the scary dairy of exceptions, you can do something shorter, which is like does the allocation like on the stack as well, may throw deserialize packet of type packet from the bytes. Modular and efficient code, the next section, or a couple sections down, I think, where it talks about embedded C challenges for design choices and testing, it really talks about this in more detail, but with Fin, you don't have to worry about writing code for single or multi-instance, and you don't have to worry about implementing vtables. Fin will generate those for you, but only when they're actually needed, not all the time. Whew! We made it, everybody! Sorry, I really like this stuff. I hope it's not boring to you guys. But yeah, so definitely check out the links in the description for jumping around and in the timelines too, because maybe I'm spending too long on exceptions and you don't care about those, so you can just skip over them. All right, well, thank you very much, and I'll catch you in the next one.